Okay, welcome to Surgical Robotics Lab 5. In this one, we're going to be learning about the analytical inverse kinematics for the robot. And then we'll be using that to operate through a constraint with the robot holding a surgical needle. So the goals of this lab are to understand sort of the trigonometry and linear algebra that goes into the analytical inverse kinematics. And then we can sort of leverage that to make our own specialized motion commands. So the inverse kinematics of a robot is what we use to determine the set of joints that can bring us to a desired pose. The pose having the parameters x, y, z, alpha, beta, and gamma for a SYSC DOF manipulator. And for the first part of this lab, you guys are just going to be filling in the blanks for each joint angle for like a generalized equation to show the understanding of the relationship between different parts of the robot and how their joints are calculated. But we'll be giving you guys the analytical inverse kinematic script for the mecha because there are a few differences that you guys can either choose to account for or not when you're filling in these angle formulas. Namely, there's an offset here along L3 and L4, which needs to be accounted for by creating like sort of a hypotenuse link and also a constant angle. So yeah, you guys don't need to account for that when you're filling out these joint angles because the script will work for the mecha. It's just so long as you can explain why the differences are there in your write-up. So we'll be using kinematic decoupling for this lab because the academic robot is a higher degree of freedom manipulator. Kinematic decoupling means that we're assuming that the bottom three joints belong to, or sort of pertain to the flange's location in Cartesian space, and then the top three joints are what are determining its Euler angles and rotational properties. So for that reason, the first thing that we have to do is find the wrist center of the robot, which can be done by moving backwards along the last link from the tip of the flange by 70 millimeters. And we can do that by looking at the rotational properties that we've specified. So if we've been given Euler angles alpha, beta, and gamma, we can determine the rotation matrix that belongs to the flange just by multiplying the x, y, and z rotation matrices with alpha, beta, and gamma as the respective parameters. And then we'll take the first column vector in that rotation matrix and we'll move backwards along that vector starting from the Cartesian location of the flange by 70 millimeters because that's the length of the last link. So once we know the location of the wrist center, we can determine the first angle by taking the projection that the wrist center makes on the XY plane of the base reference frame. And theta 1, which is down here in figure B, is just the arctangent of the Y coordinate of the wrist over the X coordinate of the wrist. And since we're doing this in MATLAB, and we want to know what quadrant that the wrist center lies in, we'll be using a tan 2 instead of just arctangent. Yeah. So next we're going to calculate the second and third joints of the robot, and given the offset that the Mechademic has, we can create a few triangles that'll sort of help us out. So the first one here in figure 2A, we actually don't have a joint between the elbow and the wrist center. It just displaces in two directions by L3 and L4. So we can just sort of consider like a hypotenuse link that I've labeled as L34 here using Pythagorean theorem. And then we'll also have to create sort of an offset angle because we're no longer just moving perpendicular to the previous link, sort of. So those can be accounted for or not in your calculations just make sure that you stay consistent. But this is useful because then we can use this hypotenuse L34 in the triangle that we've created in figure 2B, where we've got D as the distance from the shoulder of the robot to the wrist, and the shoulder of the robot is always in the same place because it's just straight up from the base and it rotates about itself. So that'll be 0, 0, 135. for x, y, and z. And then the wrist, we already went over how to calculate using the column vector of the rotation matrix and a parametric line. Yeah, and then we've got L3, 4 that we've just calculated as another side of the triangle, and then L2 as the last one. And then we'll use this in conjunction with this red triangle here, having sides D, which is also in the other triangle, R and S, where S is the height of the wrist minus the first link of the robot, which is 135 millimeters, and R is the length of the projection that the wrist makes relative to the base of the robot. So we can again use the distance formula for that. Yeah, so between these two triangles, there's a lot of information that we can gather. We can use cosine law to determine the inside angles of the blue triangle, and we can just use SOHCAHTOA for the red triangle. And we know that theta 2 is the angle made from the vertical here, from the second link of the robot. So we know that between this bottom angle of the blue triangle and this bottom angle of the red triangle, the sum of those two things minus pi by 2, I guess flip the sign, will be the angle for theta 2 here. So we know that the sum of all of these angles has to equal 90. Yeah, and then we can also use cosine law on this blue triangle plus or minus the constant to determine the joint angle for the third joint. So there's a little bit of wrapping your mind around what these additional constants are doing, but in the end they're sort of useful because we can create a whole bunch of triangles that we can use to our advantage for the bottom joints. So once we've done that, since we're using kinematic decoupling, we can just use the first three joints to create R03, which is the rotation matrix from the bottom to the elbow joint. And we know that that multiplied by R36 would be the same as doing like R01 times R12 all the way to R56. So that is equal to the entire rotation matrix of the robot. And the entire rotation matrix that the flange has already been determined in the step where we calculated the location of the wrist center. This is the general formula for the rotation matrix at the flange of the robot using the Euler angles. So we already know that. So we can just rearrange equation 11 here to get R36. We haven't solved for any of those joint angles yet, and it's equal to either the inverse or the transpose of R03 multiplied by R06. So when you look at the result of these matrices that we already know, you could probably just use arc sine or arc cosine to determine the joint angles, and you'll have to divide some things. But that's pretty susceptible to dividing by 0 if you have like 90 degrees somewhere in one of the matrix elements. So in robotics, it's favorable to use the atan2 function because this also determines which quadrant your joint might lie in. So what we're doing here is we're multiplying this right side through, and we're going to get just a big 3x3 matrix with large elements. And then we're going to cross-reference it with the left-hand side of the equation here, where we just have a few sines and cosines. So the top two elements in this third column vector are very useful, and then the bottom two elements in the third row vector are very useful here. You can take two elements and divide them so that one of the terms in each element will cancel out, and the other two terms contain the same joint angle but have either a sine and a cosine or a cosine and a sine. And that will allow you to create a tangent function, which you can then go over and determine which elements you're dividing by each other to put into these equations here. So that's sort of a tricky one where you've got to cross-reference two sides of a matrix equation. But in the end, you're just dividing a couple of elements to create a tangent function from a bunch of sine and cosine functions, because for each one of these joint angles, something will cancel out to let you do that. So you guys are just going to be filling in those boxes there. I would recommend doing that before the lab, just so that you can get going on the activity with the robot. But we'll be giving you the inverse kinematic script that you can run, and you can just test that out if you want, but otherwise we'll move on to the next activity. So in the next activity, we're going to use the inverse kinematic script to design sort of a few specialized motion commands that we can use to emulate a laparoscopic surgery. So basically, we're going to want to maneuver the robot so that it can operate the needle through a hole in a cup. And there are a few specific commands that we need to be able to use in this lab, which will be made clear after I run the script. So I think I'll show the activity first, and then I'll go through what each subsection is going to look like. So this is what it should look like. It'll move pretty slowly, just because I want to talk through it here. So first it's going to get to the initial position, so that it can move in a straight line through the hole in the cup. I hope I've put the cup in the right place. But once it's got itself maybe a few millimeters through the hole in the cup, it's going to have to reorient itself about the needle, because it's not really in a favorable joint position to actually get the needle to the bottom and maneuver itself. So that's what it's going to do now. And this is a command that can actually be done in the jogging panel of the web interface, but there isn't a command that Mechademic has really given it, aside from maybe movelin relative to the tool reference frame. But you need to rotate about the x-axis of the robot, and we're going to use the inverse kinematics for that. So that's what it's doing right now, just to get itself into sort of more of a neutral joint set. And once it's there, it'll insert itself to the first desired point on the base reference frame, after which point it'll move to another point on the base reference frame while keeping the needle constrained to the incision or the hole in the cup. So it's gotten to the first point. It's about 1 centimeter off the base reference frame, just so that no one's smashing the needle into the table. And once it gets to the next point, it'll stop. But unlike Lab 3, where we moved between 2 points on the base reference frame, and at the end result of each point, we were constrained to an incision, this time, along the way, we're constrained to the incision, which is sort of nice. So I'll stop that and we'll go through what's actually going on in the activity. So during that sequence of motions, we had a few things that we want to do without just using the web interface commands. We want to move the needle in a straight line along the x-axis of the tool reference frame. We want to be able to rotate about the x-axis of the tool reference frame, sort of to get a nicer joint set to operate underneath the cup. And then we've already got the inverse kinematic script, which will be used intermittently. And we need to figure out what the Euler angles of the flange should be under the constraint. And this is sort of an underdetermined problem, so there's a nice little cheat to get through that activity, which I'll show you guys. So first we're going to look at how we can get the Euler angles of the tip of the needle when it's underneath the constraint. Since we've got a desired location for the needle tip under the constraint and then the location of the constraint itself, we've actually already got the x vector for the tool reference frame, which we've denoted as having elements A, B, and C. And obviously this has infinitely many solutions because the other two axes can be perpendicular in sort of any rotation about that axis. So what we're going to do is we're going to create the y-axis to have a 0 dot product with the x-axis by just using elements 1, 0, and negative a over c. So this is what that one will look like. And then since we have two perpendicular vectors, we'll normalize them both so that they're unit vectors, and then take the cross product to get the z vector, which will be pointing straight forward from the flange. And that's like sort of an easy way to analytically determine what the Euler angles should be for the robot while it's operating underneath the constraint. You can only do that really if you have the hole in the cup, because otherwise you don't have another point to make the first vector. But you guys will be writing that into the Euler's script here, which will be in the Lab 5 folder, and all you really need to do is write down the vector operations that I just went through, and then the rest of it has been written for you. So that's what the first part of activity 2 looks like, and we'll move on to the next one. For the next part of activity 2, we're going to want to, or activity 3, I guess, we're going to want to rotate the robot about the x-axis of its tool reference frame, like so. And this is how we can do it in the web interface. We can just connect, and in the Cartesian jog, selecting the tool reference frame, we can rotate about Rx, like this. And this is what it looks like with the robot. So you'll recognize this from the first part of the movement from the script that I just ran. And you could probably do this using moveLin relative to the TRF with the Mechademic. But since we're in the inverse kinematics lab, we're going to do it ourselves and use the move joints command. So this is how you can do that. So we have the needle that's just been inserted into the cup, and we know that we have a different set of Euler angles for the first point on the base reference frame that the robot wants to go to. So we have the initial rotation matrix, which is the multiplication of alpha, beta, and gamma with their respective axis rotations. And then we can also determine what the rotation matrix is of the needle tip when it's at the first point. And since we're rotating about the x-axis of the needle, and that's it to get there, we know that the only difference between the two is that the initial frame here has been rotated by an additional degree theta about the x-axis. So we can rearrange this equation to get rot x is equal to the inverse of the first rotation matrix multiplied by the desired rotation matrix. And it says here to create an arctangent function to solve for theta. So this is the exact same as the second set of the last 3 joints in activity 1. So you can do this the same way as you did these guys. So down here you've got one 3x3 matrix is equal to another 3x3 matrix with large algebraic elements, and you can determine which elements to divide by each other to cancel some things out and derive some arctangent function. So yeah, you'll do that, and then I've provided the script that's actually going to execute everything, and we're just lin spacing this theta and doing the inverse kinematics at each interval, sort of, which is why it was moving so slowly initially. So this is what that's going to look like for you guys. It's called static rotation. So this is the file that you'll be navigating to. And all you're doing is creating the arctangent function here. It takes 2 input rotation matrices, the initial Eulers, which are these guys, and then the desired Eulers at the first point along the base reference frame, which are these guys. And you guys will just have to fill in this blank. This is what it looks like for me. It's just a big arctangent function, and I've got a whole bunch of multiplication and additions of the elements of the 2 input parameters. So that could be useful. And yeah, after you've made this function, you'll have made two helper functions. So you'll just be filling in the blanks in the main script, which is going to execute the entire activity. So I'll show you what that looks like. This is what the entire script looks like that you guys are going to be filling in some more blanks for. It's pretty much just running the entire activity that you just saw, except you've got to decide which function call is appropriate for which set of underscores here. And I've given you guys some hints with comments as well. So yeah, you guys have made some helper functions. They're called static rotation and lab 5 Eulers. You'll be looking at calling either of those two functions or the actual inverse kinematic script for each of these blanks. And if you've done it correctly, I'll come over and check it out, and then you guys can run it, and it should do the exact same thing that you saw me run earlier. So here's my script. The only difference here is that I've sort of made it plot the joint values along the way. I think that there's an issue with it, but it'll be helpful to see anyway. So if I scroll through here, you'll see that I've filled in the blanks and removed the comments. And when I execute this, you'll see what I've got sort of. So when I run this, it should plot the joint values for you to see. I'm just going to go to the web interface and zero the joints of the robot first. Cool. So I'm going to run this script for you guys. I guess I'll have to disconnect. First it'll pop up like this, and you'll click on it for it to start. And I've started plotting the joints just so that you can see how it should be moving. And there are some cool things to observe here. It's going to move really slowly again. But these joints will be representing what's going on with the robot here. I think I moved the cup a little bit. But you'll notice when it starts to rotate about the needle, it sort of changes directions halfway through. And that's because there wasn't one direction that was more appropriate to rotate about the x-axis than the other. So when we go back to the screen over here, we've got these joints here going to one of their limits and then coming back down in the opposite direction because analytically it was hard to determine which direction was better. So we sort of made the mistake and then compensated for it. Yeah, and the robot's still going through its stuff. So if it was confusing before at all, you've got the initial Euler angles of the robot once you're in here. And then you've got another set of Euler angles that is favorable for the first point that the robot's going to move to with the needle tip when it sort of puts the needle deeper into the cup. So right now what you're doing is that rotation about theta. So once you've executed all of that, hopefully the robot does what it's supposed to through the hole in the cup. There's going to be a report. This is going to be a more formal one where you should be describing sort of the theory behind the analytical inverse kinematics, and then describe which motion commands were doing what and sort of how they were implemented. I've said attach MATLAB files here, but Brightspace will probably only accept one submission from you guys. So if you just submit some screenshots, that's fine. If you want to attach the entire script for everything, just put it all in one zip file. But yeah, good luck in the lab, guys.